dive into the presentation directly. I hope you can like see it properly. Okay, I'll continue.
Yes. Yes.
So yeah. Okay, so this is the outline of my presentation. So I'll start with a very brief introduction to radio astronomy. Then I'll go into an overview of the SKA Kilometre Array telescope, explaining what are the science goals, the timeline, and I'll go into a bit of detail of the signal processing involved in the SKA. So I was mainly involved in mid-frequency array, so I'll briefly touch the low-frequency array telescope, but go into detail about the mid-frequency array. And finally, I'll explain the challenges faced by the radio telescope due to radio frequency interference. Oops. So, and finally, I'll state my summary. It was not a very, the radio astronomy is not a very old science. So it was like just less than a century. So in 1932, while developing some radio receivers for the Bell laboratories, Carl Jansky noticed that when he point his telescope to some part of the sky, and he get a very strong signal, and he was puzzled by that, and he casually mentioned that to one of his astronomy friends, and he noticed that the periodicity of this signal is not 24 hours, sorry, but 23 hours and 56 minutes. And his friend correctly realized that's the sidereal time, where when we rotate around the Earth's axis, and that's the time to get the same source over our head. So, and then he marked this signal as star noise. However, unfortunately, he was not allowed to continue his studies in Bell Labs, so he was diverted to different projects. But Gott Reber got heard of this observation and build himself a telescope and start repeating Carl Jansky's observations. So what they quickly realized was because of the larger wavelength of radio signals, they need to have bigger structures, and also because of the weak nature of the signal, they need to have big collection area to have enough signal to suppress the receiver noise. So, and in 1946, Martin Ryle, Joseph Pawsey, and Ruby Pine-Scott came up with the idea of the radio interferometer to synthesize sky image. So this is based on the Van-Sittert-Zernike theorem. And in 1967, Jocelyn Bell and Anthony Hewish observed the first pulsar. So they initially attributed this phenomena to little green men, but later they discovered this is like a natural phenomena, not caused by any extraterrestrial intelligence. So I'll very briefly present the principles of the operation of radio telescope. So here we have a 2-element array, and there are 2 dishes pointed at the same position in the sky, and they are receiving the observing the same source and getting the same signal wavefront. So you can see the dish in the right receive the signal first, and the dish in the left receive the same signal with a delay of Tg. And when these signals get amplified and sent to a processing, and the first signal, the signal from the dish at the right is delayed in order to align the signals of from the 2 dishes, and then they are correlated and integrated. We can increase the signal to noise ratio of this signal that coming from the celestial source against the noise of the receivers. So so that's the basis of that. And then there's a theorem called Van-Sittert-Zernike theorem, So it shows that the 2D Fourier transform of a celestial sky brightness, or the sources of the sky, gives us the field intensity on a plane like the surface of the Earth, like projected surface of the Earth. So that can be used to generate this these sky images. Like if you take the cross correlation of the signals at different points and grid them accordingly, and then take the inverse Fourier transform, voila, we get a image of the sky. And this is the underlying principle of aperture synthesis. So, and also in order to get a good grid of these cross correlation points, the orientation of these antennas are important. And so here you see arrangement of the very large array at New Mexico. So it has kind of a Y shape, 3 arms at 120 degrees apart. So because of the rotation of the Earth, you get different points, different positions relative to each other, as shown in the middle picture. And also because we use different frequencies, so then the spacing can be different because the resolution for different frequencies or wavelengths are different. So then you get multiple points that you can be used to generate your Fourier domain image, and then converted it to the like the sky image. So this is very basics, very like 10,000 foot overview. So let's go to the SKA. So when in early 1990s, so there was the scientists, the radio astronomers, wanted to observe more and more, be more sensitive, like observe very faint phenomena in the universe. So they floated this idea of having 1 million square meters of collection area. So you have this huge sensitivity to observe the signal. So the initial thinking was, okay, just give us the collection area, whatever, like just collect the radiation coming from this these sources, and then the DSP will take care of the rest. So, but they realized that it's not the case. So just the collection area would not do. So then they have to fall back to different, actually the conventional method. So, however, so this idea, like the just having the collection area, led to some interesting projects like the Large Adaptive Reflector, which was conducted by the DRAO, where I work now, and then also the phase aperture arrays, also focal plane arrays, where myself and Chamira worked for our undergraduate, graduate degrees. And also the dense aperture arrays, you can see the diagram here. So, but they hardly matured to be used as radio astronomy observation systems, because the noise are too high, either signals are not stable, and so on and so forth. So, so some like scientists basically had to fall back to the conventional methods in building the SKA. So again, like when you're building a SKA, you have to ask for money from the politicians. So you have to show some quantitative figures, why do you need them, and like why it's better than the existing one. So this diagram shows the figures of merit for the SKA. So you can see in gray, the existing telescope, LOFA from Netherlands, low frequency array in Netherlands. UGMRT is the giant meter wave radio telescope with upgraded. So it's based in India, I think in Western province near Mumbai. And JVLA is a Jansky very large array that I mentioned earlier in the talk, about located in New Mexico. So if you consider that, so the sensitivity is like defined as the effective collection area of the telescope divided by the system noise temperature. So noise temperature is the noise generated by your receiving system as well as the sky noise that affect the low frequency. So the SKA1 is expected to have about like 10 times more sensitivity than the existing telescope, and the SKA Phase-2, the full system is expected to have about 100 times the existing sensitivity. Another figure of merit is the survey speed, because the scientists or astronomers want to have their, like, because their prices, because the Nobel Prize is not awarded posthumously, because then they have to have it when they're alive. So they wanted to have complete their observations of the science in time. So the survey speed is how fast you can get an image of the sky. So this is defined as the sensitivity squared by the field of view. Field of view is the area of the sky that you can look at one instant of the time. So this also shows that the SKA and SKA2 are about like order of magnitude better than the existing radio telescopes. So further figures of merit. So this is the earlier ones for the imaging, and this is for the pulsar observation. So you can see, but SKA is on par with the FAST. FAST is the 500 apertures spherical telescope that is built in China. It was completed in 2016. And that's a very big stationary telescope. So that built on a natural setting in the ground. So, and also you have Arecibo here, which has been like destroyed later last year. So, and also you can see SKA is leading in that department also. So okay, so another figure of merit of the radio telescope is the resolution. Resolution is how finer you can see or observe the sky. So that depends on how far away your elements are spread. So in order to have this one, there is called the VLBI network. So very large baseline interferometry. VLBI stand for that. So an SKA along with the global VLBI can be as far as, because already there is like VLBI radio telescopes in the world. So they do the interference, so you can be at far off, but you can greatly increase the sensitivity with these new receivers and digital signal processing. And also here you can see SKA is leading the radio frequency. Actually, the current design does not go as 30 gigahertz as shown here, but more like 15 gigahertz. So it would be something like here. Like that, but even still the angular resolution is order of magnitude to like half order of magnitude better than the existing radio telescopes. So yeah, that's the objective. Okay, so let me see. No. So yeah, so SKA is going to have in twin site. So the SKA low frequency telescope is going to be in Western Australia, so which is observing 50 to 350 megahertz of band. So yeah, so and so it's also the site also contains the Murchison wide field array, which is actually a precursor for the SKA low frequency telescope. And also it also hosts the Australian SKA Pathfinder, which consists of 36 dishes. So as you can see in this figure, you can see a spiral shape. So so that's also the shape is to get that UV plane or the Fourier plane filled nicely with the rotation of the Earth, so that it won't give you blank spots or the sparse areas when you do the Fourier transform. So on the right, you have the SKA mid-frequency telescope, which is mainly based in South Africa, and having a remote station in all over the southern part of the Africa, and also goes to Madagascar and Mauritius too. So and also co-located with the Meerkat, which is the precursor for SKA mid telescope, and here another telescope that observes the hydrogen density in the the mid telescope observes from 350 megahertz to 15.4 gigahertz in the current design state. So so the site selection is due to like the RFI. So basically, you go for the remotest place where the least human activity is possible, and then you try to have your telescope there. But you need to have infrastructure. You have to have lots of power and accommodation for people working and doing repairs and installations there. But still, you prefer to have the remote. So if you look into these maps, these are deserted areas in respective countries. Population densities are very low, so you can see them. Like Murchison area population is 4, and still you have some RFI, basically due to military and satellite communications. And if you look at the Sydney, you see it's impossible. Like the radio spectrum is completely covered with RFI. And even in the left figure shows in the site of the Karoo for the SKA mid, you have some RFI due to UHF and digital TV, and also mobile communication around the 1 gigahertz signal range. And if you go a little bit further, you'll see downlinks from GPS satellites. So yeah, that's the key reason for the remote site selections. And also the SKA site, one of the requirement is to keep this areas radio quiet zones. So you can see the governments have enacted legislation to preserve the radio quietness. So they limit the activity conducted in these areas. You see these warnings, and so you need special permission to do that. And however, with the use of, as I mentioned, I'm going to mention later in my presentation, the mega clusters of low Earth orbit satellites providing internet services are going to be a huge challenge for a telescope like the SKA. So, so that's the completion of the overview so now let's move into the science goals. So there are categorized some science goals for the project. So one is the galactic evolution, cosmology, and dark energy. So that's and then they're going to test Einstein in his general theory of relativity with strong field of gravity using pulsars and black holes, and also origin and evolution of the cosmic magnetism. That's it's a really interesting topic because only radio telescope can observe the magnetism. And probing the cosmic dawn, the cradle of life, the most popular among the citizen scientists. And also you get surveys because the southern hemisphere is not as highly mapped or regularly mapped as the northern hemisphere. And also another emerging area is the study of radio transitions and fast radio bursts. and also having the flexibility to observe like new phenomena that we don't know already. So I'll go into details a bit about these science goals, just to give you a brief idea. So in late 90s, Georges Latimer and Edwin Hubble independently discovered that the universe is expanding and the expansion rate is accelerating, moving away faster and faster from each other. So this acceleration caused Einstein to like even change his famous equation to re-enter the cosmological constant. So he was so that's considered his greatest blunder. And astronomers use the Doppler effect, the redshift when because they believe that all the matter in the universe are the same. They have the same spectral properties. So if you see some shifting of the frequencies of the radiation, they see it's due to a Doppler effect. So then because the that galaxy is moving fast away from us, so then they use that properties to measure the speed of speed of movement of that galaxy. So, and these can be like, you can look into further galaxies using the increased sensitivity of the SKA. So, and another thing is the gravitational wave. So we have this LIGO testing the gravitational fields of the world, the gravitational waves propagating and all that. So, however, these are very, very sensitive tests, and it's very expensive to do. But however, you can, because of the astronomical size of the universe, the pulsar timing techniques can be used to observe these phenomena at different scale using the SKA. So that's another topic that the SKA going to be a leading in science in verifying the Einstein's general theory of relativity, or either disproving or proving it using the strong field test of gravity using pulsars and black holes. And another topic is the cosmic magnetism. As I mentioned earlier, the magnetic properties are not observable with the optical telescopes, at least not easily. Like the universe is filled of strong magnetic fields and all that. So, and you can use different phenomena like synchrotron emission, Zeeman splitting, and Faraday rotation to observe the polarization properties and map them accordingly, and to get a better understanding of the universe. And this also the increased sensitivity and all the polarization, purity, and ability to do those measurements would get SKA really good, will make him a very good position to help astronomers do their science. So again, this is the evolution of the universe and studies. We have baby pictures of the universe just after the Big Bang using the cosmic microwave background, but from that, like 13.7, 13.6 billion years, and up to like about 13 billion years, we don't have much data what happens there, and SKA would be using the structure formation and reionization observation to determine what has happened in those areas and get an idea about that. So, and again, the famous one with the general public, the search for extraterrestrial life. So, unlike we won't be able to like listening into and decode signals for like intelligent broadcasts. The SKA main looking into the spectroscopy of the signal to determine whether there is like chemical activities that can attribute to life. So that's the one. So there was an article a few months ago about some scientists discovering the traces, like the spectral signature of phosphine in Venus's atmosphere. But later it was kind of debunked or like disproved because they use a kind of shoddy method of fitting their data into the category. So, however, there is some in order to please the public, the SKA is also state that it's sensitive enough to detect an airport radar from a planet that's 50 light years away. So, like that, so it's keep you interesting. Okay, so as I mentioned, the 10 to 100 times increase in the survey speed and the sensitivity help to make continuous maps updated and cataloging millions of radio sources around the world. And also another emerging area of study is the radio transients, where we see signals ranging from 1 nanoseconds to several years, changing the strength. So that's also another interesting area of study that attribute to rotating radio transient and gamma ray bursts, where for the SKA. And in 2008, some 15 member countries signed a memorandum of understanding to work towards the SKA. And in Australia and South Africa became contenders for the site. So earlier they were contending, they were planning for both telescope to be in one location. So they conducted their own studies. So the Australia started Australian SKA Pathfinder. The image you see here, so it's 36 dishes. And also they have already had some tiles of the Murchison Wide Field Array, or the MWA. In 2012, the governing board at that time went for a split decision to divide the two telescope into the two contending countries. Okay. So the SKA Low went to Australia and SKA Mid went to South Africa. And in 2011, the South African radio astronomy community gathered to construct the Meerkat, a 64-dish precursor for the SKA Mid. And then after the site selection, the SKA governing body formed 16 consortia to study different aspects of design of the SKA. So I was part of the low frequency aperture array consortium while I was in Curtin, Australia. And then when I joined the NRC, then I moved to the Central Signal Processor Consortium. So, and there were others like science data processing, and also telescope manager, infrastructure, and so many more. So, and between 2014 to 2018, there were so many engineering meetings and technology interchange meetings, and there they discuss different the advantages and disadvantages of the different technologies shortlisted for the SKA, and then they come up with costing. So, and then because of that, the governing board realized that cost is going higher than the initial estimate, and they went for a rebaseline. That means they scale back the design for the SKA1. So they cut about 30% of the dishes from the SKA Mid and half of the element from the SKA Low. And then they start again doing the same practices of costing and technology discussions. And then from 2017 to 2018, they had sub-element critical design reviews. So they would like kind of formalize the design and then like finalize the costing and all that. So, and then in 2018 to 2020, they had the system level critical design review where they considered the telescope as a complete system in order to get an idea. So from 2018 to 2020, different countries like Australia, South Africa, Netherlands, Portugal, Italy, and United Kingdom ratified the Intergovernmental SKA Observatory governing body, so that securing funding for the project. And then they just had their first board meeting in February this year. So that's the timeline of the SKA so far. So yeah, so SKA Phase-1, after rebaselining, you have like 512 stations consisted of 256 elements. The maximum baseline was reduced to 65 kilometers from 80 kilometers. And as I mentioned, observing the band of 50 to 350 megahertz. And they use these dipole arrays in order to receive the signals. In SKA1 mid, you have a total of 197 antennas, and this contained the 64 existing meerkat dishes with a diameter of 13.5 meters, and they're going to have 133 new SKA1 dishes of diameter 15 meters, and the maximum baseline is 150 kilometers. So for the mid, the observation bands are band 1 for the Phase-1, the band 1, 2, and 5 that covers the frequency range from 350 megahertz to 1.76 gigahertz, and also from 4.6 gigahertz to 50.5 gigahertz. So this is kind of the architecture or the structure of the SKA telescope. So in the left, you have the Australian low frequency array, and right, you have the mid frequency array. So you have the base, like the main core signal receivers, and they have several remote stations, and the signals received from the core array is sent to the central signal processing through the signal and data transport, and then you do some processing there and send the reduced number of data lines to the science and data processing for making images, or and then archiving, and then you have distributed those values to the regional data centers to do further processing. So you have the similar architecture for both low and mid. So these are the signal processing step for the SKA low telescope, SKA1 low telescope. So you have the low frequency aperture array where you do some initial signal processing. You have antenna arrays. You do you get the signal, receive the signal, do some analog signal processing, like filtering out the out of band signal from 50 to 350 megahertz, amplify, and then you digitize the signal. So here you do like about 8-bit digitization and do some processing. You channelize it to 512 channels of roughly 1 megahertz of bandwidth. And then these channels have been bundled into fiber links and sent to the central signal processing facility, where they undergo further processing, get further channelized, and then you do delay tracking. Remember in slide 2, I mentioned you have to compensate the delay in order to get the positive correlation. You do so in apart from the correlation, you also do beamforming, where you add the signals with delay matching, so that you get a signal a stronger signal at the end, and those beamformers are used for parser search and parser timing. And after that, you do like the cross correlation and beamform signals, and then after doing some parser search and parser timing signal processing, they go to the science and data processor. So they do further. So science and data processor is responsible for formation of images, and calibration and so on, and then archiving the data, and also keeping the record of the parser data and parser catalog, and then those details go into regional centers for further analysis. And also there is a synchronization and timing distribution, because you need an exact timing in order to get an exact match of the delay in order to get a positive correlation. This is really a deep study area of study. So I'm not going to go into details about that, just to mention that. So it has to be taken and considered as a really important part of the radio telescope, which is also part of the observatory clock system. So where you keep record of all the events and the timing of the telescope, so that they can be used for science properly. So yeah, and you have telescope manager, which kind of controls the entire systems, that planning the observations and handling faults and so on, so forth, and keeping the records of all the systems, monitoring and control and maintenance. Sorry. So this is a signal flow graph of the low frequency aperture array. So you have these elements, and this signal received by these elements, like they have two polarizations. You get fed into an amplifier, then a low bandpass filter, actually is, and then again some amplification, and this is an electric to optical conversion. So the in order to reduce interference, so the signals are sent to the processing block as an optical signals, and then again it's converted into electrical signals and do some analog filtering just before the digitization, and then these digital signals get channelized, and then those channelized signals are combined in order to form a station beam, so that you can point the signal, observe a certain part of the signal with high signal to noise ratio. And so you have tiles, multiple tiles. There are 256 elements, and tile processing module processes about 8 of those. That means you have 16 of 16 antennas. So there you have 16 of these tile processing modules of that. So yeah, so they do some initial channelization and beam forming at the station level at the LFAA. So, and yeah, so this is the signal flow graph they do. They have a delay in order to match, like a delay in order to match the delay, and you have a polyphase filter, and you select some channels, and you do a phase delay in order to like do fine delay adjustments, and you apply the calibration amplitude and phase, and then you combine those channels from different elements to form the beam, and then you get some other beams like channels from other elements and combined forming partial beams altogether. So this is the low correlated beamformer architecture. So you get the signal from the low frequency aperture array and do some kind of analysis of the signal to see whether you are getting the signal correctly, and then apply some further delay and some further phase corrections in order to. And there are 3 signal processing path processed in the low CBF. So you have imaging pipeline, and there is a PSS, parser search beamforming pipeline, and the parser timing signal processing pipeline. And here they use the same parser timing pipeline to use very long baseline interferometry signals from low. So in the imaging, you have phase correction, and you have a channelizer and apply another phase correction. And also, as you can see, RFI is a big problem. So you analyze each and every channel coming out of this channelizer, and then flag them if they suspect to be containing any RFI, and then you correlate, you get all the channels for this given frequency, and you combine them and cross correlate, and you take the output. So these outputs from the correlate are called visibilities because they are used to generate the images. So those goes to science and data processor directly. In the parser search pipeline, you have a channelizer, and again some fine delay correction using a phase rotation, and also have RFI flagging and station polarization and PSS like that. So that's the idea. I think I'm lagging behind, so I'll speed up. So this is the arrangement of these signal processing blocks in an FPGA. You have like the packets coming in using 100 gigabit Ethernet, and you use that, and then use high bandwidth memory of the FPGA to make the coarse delay correction, and then use signal processing to do the other processing there. So, and use, so PCIe interface, 100 gigabit Ethernet, and so on and so forth. So so one of the key questions that they have been formed is the custom hardware versus commercial off-the-shelf product. So custom hardware is costly, but they can do a specific job very efficiently. The commercial COTS hardware is relatively cheap. You don't have to do, and the development environment is already there. However, sometimes the specifications does not agree well with your requirements. So so I'll go into detail of the MID telescope where I work. So you can see you have the dish antenna, you have some feed hardware where you get the signal like cryogenics. That means you have to cool the signal to avoid the signal get corrupted with noise too much. And you have RF electronics to amplify the signal. And then you have some digital signal processing for some channels, some bands. So you extract the desired part of the spectrum from that. And you have encoded these signals into the long haul fibers to be carried to the central processing unit. So, and in the central signal processor, we have a similar structure. We channelize and beamform, and you feed these channelization signals for parser search and parser timing. And also we have a different VLBI pipeline for generating these VLBI signals. And you have the same science data processor archiving and processing, further processing these signals. So in MID, we use an architecture called the Talent frequency slice architecture. because you have seen in the low frequency range, there was only just one band. So it's easy for them to use it. And we thought that would be easier for us if we can make it like that, because even though we have different size bands. So what we do is we pre-process the signal from the what we get from the antenna, and called the using oversampled polyphase filter banks called very coarse channelizer, and generating bands that are about 200 megahertz wide. So these can act as like a single channel device irrespective of the band, and then we can use the same hardware downstreams to do different sort of processing, like generating visibilities using cross correlations and pulsar search beams, pulsar timing beams, and VLBI beams. So the idea is to have some overlap, because if you just channelize and because of the channel response of the channelizers, we might lose some part of the spectrum because of the transition bands. However, we avoid that by using an oversampled polyphase filter banks, where you get some overlap between the channels. So as you said, we have 197 antennas, but we designed the system for 200 antenna, so that we have some extra just in case of failure. So these are the signal chain for our system. So as I said earlier, we have an imaging signal chain going here, and also pulsar search and pulsar timing and VLBI. So one of the responsibilities for me was to verify the signal chain of the mid correlated beamformer. So what I did was I had an end-to-end signal model for the signal processing units of the mid CBF, and then I designed filters according to the specifications and fed synthesized signals through them and end-to-end, and try to create the realistic signal chain from there. So to see whether we can achieve the required sensitivity and noise levels and decorrelation, minimization, so on and so forth. So these are some of the results that we got from this the modeling study. So talking a little bit about the hardware to do this process. So so for us, we didn't find any COTS hardware to have enough bandwidth to do our processing, at least not for at this moment. So we have to develop our own custom board called the Talent DX signal processing card that features an Intel Stratix 10 FPGA. So we came up with the architecture, and also we use optical circuits in order to cross-connect these devices. So, and our idea is we have VCC units, and then we use optical fiber connect that to the FFC unit, where we do the band independent or band agnostic processing, and the band specific processing is all concentrated to VCC. And another feature of this architecture is that we send back the signal where it comes from in order to balance the input output capacity of each of these cards. So this is another expand view of that architecture, a little bit more clearer. So the same part. So this is the arrangement, and the idea is you would have like you need about 370 LRUs to process the signals for the SKA1 mid. So that requires 20 racks and consumes about like 272 kilowatts. And it cost around 30 million euros. So roughly split between hardware and the labor. And the construction timeline is mid 2021 to 2027. Okay, so I'll go into the details of the RFI. So here you have like a calculation of the ray tracing method using in the like featuring the GSM base stations around the core of the SK mid and how powerful of the signal. So according to the regulations, you have to be at least minus 110 dBm in the core and the site of the vicinity. But this calculation shows many of these antenna like dishes in that area is not in that level. So that can be a further hindrance of the utilization of the SKA for the observations. So, like if you have a strong signal, like we can't see stars in the daytime. So if you have a strong signal that completely saturates our system, so making us like the radio telescope blind or saturated for the faint celestial signals. So this is another feature. So this is called a waterfall plots spanning 48 hours. So the interesting part is you can see there are like some radio frequency interference. I think these are like GSM in the first line, and there are some signals that are missing during some part of the day. So you can see, I think these are the navigational aid signals emitted by the airplanes traveling ahead of the observatory. So, and again, in the right part of the observation, you can see the interference caused by the satellites where almost present. So, and also if you have this ionospheric effect, you can see the radio interference would be coming from further away places. You can see from the black diagrams. Yeah, this feature is called ducting, where the RFI signal is carried further away due to the ionospheric effect. So normally it's about like 7 to 8 dBs lower at that time, but it get increased due to this ducting effect. So in order to cater this, so we have RFI detection and flagging. So where we do a running average study, and if the running average exceeds the given set threshold, we flag that and mark it as a frequency. And then because the radio astronomers doesn't want to deal with any contamination, and as far as now, they are patient enough to throw out even like half of their data collected in order to have some kind of pure signals, like not contaminated with RFI. So that's the idea behind that. We just mark it and then say, okay, don't use this for your science. And this is like a explanation that I use in my simulations to see how will this affect that. So I created a saturated signal, and due to the saturation, the signal gets clipped, and then this could result spectral leakage, that you see a spectral component that's not supposed to be there. So And in order to avoid that, what I do is I kind of look into this and mark them, don't use them. And when you progress it across the signal chain, you have to extend, because the filter banks kind of extend that signal. So you have to do those, keep those signals out of the correlation. So here I show an extension of the flag. So this is the frequencies and the expected intensities of some known RFI that we simulated and studied. These are some simulation results with no RFI, some RFI with that always present. And these are you can see the earlier ones are somewhat concentrated into one region, but you can see some spread all across the spectrum. And some even cause some splattering across the spectrum too. And the biggest challenge I can see is for the scale type radio telescope is the mega constellations providing the internet. So there are at least 3 service providers up to now that would plan to send thousands of low Earth orbit satellites to provide internet service all around the globe. So soon it won't be possible to observe the sky even without seeing at least one of these satellites in there, like the main beam. So, and to make things worse, so at these frequencies, about 6 gigahertz to 15 gigahertz, there aren't many ADCs that can have higher dynamic range, so that we can observe the full signal and do filtering, digital filtering to remove that. And also the analog filter, and the analog signal chain also is not linear enough to withstand the high dynamic range. So it makes it very hard to control this. So as a remedy, I know that National Radio Astronomical Observatory of US had an agreement with Starlink. So Starlink would like turn off their downlink when they pass through or go ahead of observation. So the SKA should have a similar kind of plan or agreement with these satellite service providers to avoid completely being wiped out in their observations of those frequencies. So in summary, I would like to say that the construction is in full swing for the SKA Kilometre Phase-1. So the intergovernmental governing organization of the observatory has been ratified, and then and also some other countries are considering, at least at different levels of membership. So the design work is completed, and the design plan and costing has been reviewed by an expert panel, and it's going to get built. However, the interest in RFI, because of the terrestrial 6G wideband communication, as well as the in the sky contamination, can severely impede the observer or limit their ability to observe the sky with the given sensitivity. Okay, thank you very much for your patience. I hope I didn't rush through at the end and got some idea of the radio telescopes, like the scale, the current position. And if you have any questions, and if you have time, I'm open to.
Yeah. Thank you very much, Dr. Tara, for your very important webinar on this topic, actually very detailed one, especially the signal processing chain. So I would like to thank you again. And so I think we have several questions. So the first question is, are there any applications of compressed sensing in this field? Would it make it possible to reduce the size quantity of the arrays?
So the thing is, this is being very like widely discussed or debated topic. So one of the things is uh, the the scientists, they don't want any, like they want the least amount of kind of altercation of their signal. So if we do those kind of compression and some process of signal processing that does not give you like the exact representation, because when you do a compressive system, there is always some loss of the signal. So they believe that there can be some distortion involved. So that's what the reason for they would go for complete like a blackout of the RFI, not trying even to filter it out, because they suspect even those can impact their observation. So, but in some applications, I think they also use this compressive sampling in radio, not exactly in radio telescope, but in some cases, especially with I think when they kind of archive these images and so on.
Yeah. So basically, this is also with the actually this sparse arrays. I think this, so rather than using this large number of antennas, could we have a small number of antennas and try to go with some other algorithm? So that kind of thing.
Yeah, so there's a different like phenomena. So there's one called large N small a type. So this is SKA is a large A small large N so small a type antenna. So because we improve the resolution because we can move like we can place the antennas further away. So there is that, and so, and also you can keep the collecting area high by having a large number of dishes concentrated in the core region. So, and there are also small n, large A, like the single antenna telescopes. So they have a different area of science. So some science applications require different types, but in general, large N, small A type telescopes can handle almost handle like in general, you can handle those observations.
Yeah. So the second question is actually, it is a more general question actually. So what type of subjects electives should I take to get a better job of this field? Yeah, because astronomy is not actually very popular in Sri Lanka. So
yeah, so if you want to go into radio, like my job is like a signal processing or the instrumentation engineer. So I work on signal process. So I think the signal processing chain is so I work in like Fourier transform, random signals, and studying the quantization effects, delay, filter responses, and so on. So I think your curriculum is, I think I have the basics of those. And also I'm involved in the digital design, configuration of the FPGAs and those kind of things. So this is like they have the design part and the implementation part. I think the basics are well within your electronics and telecommunication curriculum. So if you want to go into the science and you need to have a detail of physical nature, you need to have a details understanding of the physics, at least the astrophysics part. Yeah, so, and also there is a lot going on with machine learning and artificial intelligence in like RFI mitigation. So currently, so I showed you a very basic, so because we implement this RFI mitigation method in a very low intelligence areas where we just have, in the FPGA, we just have a few multipliers and all that. We don't have much intelligence or the control ability there. But when it comes to down the pipeline in the STP side, where the data rates is much lower, and you have like the usage of high performance computers, so you can use machine learning and artificial intelligence in order to identify and flag RFI from multiple regions. So because as I showed you earlier, sometimes like RFI in one region can cause like spectral leakage in some other region, and you have to have a somewhat like good catalog of these signals and phenomena in order to like flag them and remove them from your data accordingly. So
yeah. Third question is something similar to what you have already explained. So are there any use cases of deep learning in this field?
yeah, so it's like sometimes, yeah, so again, like it's one is like RFI, like it's more general area, so you remove it. And also there are deep learning curves in identifying the patterns and all that, so you study like the gas explosions and all that, those kind of observations. So study the observations too you need, and also the variation of the pulsar timing periods due to the gravitational waves, or the change of the space-time fabric. So that's also another area to use these like deep learning, machine learning kind of things.
Yeah. So actually, those are the basic questions from the audience. So actually, I have a few questions. So basically, yeah, I and you worked actually on the dense aperture arrays and the focal plane arrays about 10.
Yes, I mentioned that.
Yeah. So these dense aperture arrays, are they used in the SKA now? Or you mentioned that.
No. So that's another, like I think Netherlands kind of have a prototype arrays. I think what happens is it's kind of too computational complex to implement that. And they are also targeting same frequency range as the SK mid, at least in the lower band, like from 350 to like 800 megahertz. So I think there's not much of a like a difference in performance using the mid dish-based receiver as well as a dense aperture array.
Okay, yeah. So the same happened to the focal plane array, right? Is it so? Now it is element or is array? Yeah.
So that's a focal. So like here you use a single element, because the focal at the time of like when they finalized by 2016, they finalized the dish receiver, the focal plane array. So now they call like the phase aperture feed.
Yeah.
So they were having like higher than expected noise.
Okay.
So then they, like this, as I mentioned, they went with the conventional method, the cool cryogenics, cryogenically cooled receivers for that one. But the fast has Australia has been developing this checkerboard array, I think, and with like squares receiving, and they have been developed, and the 500-meter telescope in China, they have been equipped with one, and also the single dish telescopes have better luck with those these phase aperture arrays, because of the high signal to noise ratio, the high signal intensity that they observe from those dishes. So
yeah. Okay, so in this case, so the beam forming will not happen at the let's say the
element
level.
No. So
it will happen as selection, right?
Yeah. So the element, the receiver or the horn would act as the analog beamform.
Okay, yeah.
in this case. So,
Yeah.
but
So
we have found beamforming, like combining the signal from multiple dishes to form like a finer beams. To
yes, so that
observe
is
pulsar.
basically a delay. And some are you going for a more?
No, it's delay and some. I think
Yes.
because of the irregular shape
Yeah,
and
yeah.
the
Okay, yeah. And the one thing, yeah, one last question. So the basically with your experience, yeah, in Sri Lanka actually we are not working very much in the radio astronomy, and
right.
we have started some RF related work, and so basically with your view, if we start some research or some development, what would be the best idea? Because we have a limited budget and those kind of things. But in
Right.
research work, what are the best things? Yeah, for a Sri Lankan university or students work on?
Oh, so yeah, so the RF parts, yes. So I'm also not very familiar with the RF signal chain. So like my area is like so the digital signal processing part.
Yeah.
So it's so one of the things is I noticed is like there be like now you have this like high level language based digital signal processing for FPGAs, and then and configuration of the FPGAs and programmable logic. And also, like as I mentioned, there are COTS systems that being developed by like FPGA vendors that has pretty good capabilities, even though maybe not perfect, but they, so I think it's kind of like an if you can possible, that is a good way of like studying or getting experience on doing these high level languages and doing optimizations for the digital designs. For the RF parts, I think the bottleneck is in devices like the synthesis of this, and you need a kind of expensive fabrication simulation methods in order to have a level of sensitivity for the next generation telescope. So it's good to have experience with these things, but to make an impact, you need a little bit more money than I
That is true.
think we would have.
Yeah. Basically, I started that work with your colleague and my colleague also, Arjuna Madana.
Yeah.
Yeah.
Yes.
Actually, so we built some small Doppler radar system actually, and